Well, friends, we're talking about Math 105, Section 4.3, and we're going to deal with some graphs of exponentials. And the dream is here to be able to think about what the long-term behavior is of both of these things. But before we get there, let's define a term. And we can say that a horizontal asymptote is a long-term stabilization of a function. So I can assume that all of you are fully grown, and what we can say is we can say let h of t be your height in inches t seconds after you were born. And if I begin to graph this, now I don't know how tall you were when you were born, but let's say you were some small version and then your height increased, and then maybe when you were I don't know, maybe 13, maybe 15, I don't know how many years old that is, I don't know how many seconds that is, but at one point you hit your maximum height and then it stabilized there. And I don't know how tall you are. I'm going to assume that you're 5'5". So in inches, that's going to be what, 65? Yeah? So 65 inches. And that's the long-term stabilization. Y is equal to 65 inches is the horizontal asymptote. Another example might be if I'm playing a guitar. Here I am, right? Here's my guitar. And my guitar only has one string, as indicated by my one tuning peg. All right, I have other tuning pegs. But so here's my one string. And let P of t be the height of the guitar string above the ground. And so let's just say that it starts out and we are 3 feet above the ground in feet. And if I was going to make a graph here, and here was 3, at first when I pluck the string, it'll be a little bit higher than 3, and maybe this is exaggerated. But it's going to be higher, and then it'll be lower, and bang, and it begins to stabilize, yes? Now, what's interesting about this one is that we have a horizontal asymptote at y equals 3 again. But here, we cross that asymptote an infinite number of times. And I think that's one of the great misconceptions about horizontal asymptotes, that you can't cross them. And oh my goodness, we cross this thing a bunch. In fact, the sleeping one you also cross, because when you go to bed, your spine expands and you're a little bit taller. And then by the end of the day, being a Michigan student, you are crushed by the weight of the world and you are a little bit shorter. And so you are constantly vacillating around this horizontal asymptote. Okay, we're going to specify this a little bit better in the next page and then talk about how this plays with exponentials. So here today, we're talking about long-term behavior. And what this means in terms of functions is we're going to be talking about as x goes toward infinity, and we can say as x tends to infinity. I guess we could talk about negative infinity as well, but so long-term behavior as x tends to infinity, as we can write it this way. Another notation of writing this would be the limit as x tends to infinity. So all of these things, long-term behavior, x tending to infinity, the words x tends to infinity, and the limit as x goes to infinity are all the exact same idea. And what we're talking about is however the function is behaving, if it stabilizes, we can talk about that. So let's go to something like exponential decay. And let's draw something. Why don't we give a possible example of this graph? If it goes through 7, we can say that y is equal to f of t, and let's say this is 7 times, and we're keep in mind that our b value is less than 1, 0.42 to the t power. Good? And that means that 42% remains, or 48% is decaying each time we are looking. And so we can say as t tends to infinity, what does f of t do? And we can see that we are getting closer and closer and closer to 0. Conversely, and I guess I could write this a little bit differently before we carry on, I could say the limit as t goes to infinity of f of t. We could say that that equals 0. And both of these notations here, this notation, t going to infinity, f of t going to 0, and the limit as t goes to infinity of f of t equaling 0 are the exact same idea. We should probably point out that f of t will never equal 0, but it's going to get as close to 0 as we want if I'm only keeping that 42% each time. Okay, let's go in the other direction. Let's go in the other direction. What about the limit as t tends to negative infinity of f of t? And what we can see here is that as we are getting more and more and more negative, our exponential is getting bigger and bigger and bigger. And so we'll say that as t goes to negative infinity, f of t goes to infinity. Let's look at that from an exponential growth problem. And if I give us some exponential growth, and let's call this one P of V. Here's V. We'll have some y-axis. And this is clearly exponential growth. We're going to have some a, b to the v. And we know that the b value here is certainly greater than 1. So now that we have that idea, we can say that as v goes to infinity, p of v, well, v gets bigger. P of v is also going to infinity. It is getting arbitrarily big. We could write that differently. I could write the limit as v goes to infinity of p of v equals infinity. If we go to negative infinity, p of v is getting closer and closer and closer to 0. And we could write that with our limit notation as well. The limit as v goes to negative infinity of p of v equals 0. So here's what we have. What are the takeaways concerning exponentials? And I guess we have some very important ones. The domain of an exponential is from negative infinity to positive infinity. I can put anything I want into any exponential, and we're always going to get a value out. But the range, we are going to be getting closer and closer and closer to 0 as we go to one extreme or the other, as we go to negative infinity for exponential growth, or as we go to positive infinity for exponential decay. And the highest value is we're going to shoot to infinity.